Imagine a world where the sun never sets on one side of the planet while the other remains in eternal night. A place where a year lasts just 19 Earth days and the sky is painted in deep red and orange hues. Now picture this world as potentially habitable. It sounds like science fiction, right? Well, buckle up, space enthusiasts, because this world is real, and it's rewriting everything we thought we knew about habitable planets. In a groundbreaking discovery that's sending shockwaves through the scientific community, astronomers have found not one, but potentially two Earth-like worlds orbiting a nearby star. And get this, they're in the Goldilocks zone, where liquid water could exist on their surfaces. But here's the kicker. These planets aren't just another pair of Earth twins. They're in a class of their own, defying our expectations and challenging our understanding of what makes a planet habitable. We're talking super-Earths orbiting a red dwarf star, a combination that, until now, many scientists thought was unlikely to support life. Yet here they are, forcing us to rethink our assumptions and expand our search for alien life in ways we never imagined. This isn't just another exoplanet discovery, folks. This is a game changer, a paradigm shift that could revolutionize our understanding of life in the universe. We'll explore how these planets were found, why they're so special, and what they mean for our ongoing search for life beyond Earth. We'll separate fact from fiction, examine the cutting-edge science behind the discovery, and peer into the future of space exploration, the traditional search for Earth-like planets. Before we dive into our groundbreaking discovery, let's recap what we've been looking for all these years. For decades, our search for habitable worlds has been guided by a simple principle: find planets that look like Earth. We've been obsessed with the Goldilocks zone, that sweet spot around a star where conditions are just right for liquid water to exist on a planet's surface. This zone, also known as the habitable zone, varies depending on the star's size and temperature. For a star like our Sun, it's roughly between the orbits of Venus and Mars. But this zone can be much closer for smaller, cooler stars. We've been hunting for rocky planets about the size of Earth, orbiting stars similar to our Sun. Our space telescopes, like Kepler and TESS, have been tirelessly scanning the skies, looking for the telltale dimming of starlight that indicates a planet passing in front of its star. And don't get me wrong, this approach has been incredibly fruitful. We've discovered thousands of exoplanets, some of which are tantalizingly similar to Earth. Remember Kepler 452b? Discovered in 2015, it was hailed as Earth's older, bigger cousin. Orbiting a Sun-like star every 385 days, it seemed to tick all the boxes for potential habitability. Or how about the TRAPPIST-1 system? This compact system of 7 Earth-sized planets orbiting a tiny, cool star captured our imaginations with its potential for hosting life. Especially TRAPPIST-1e, which is almost exactly Earth-size and receives about the same amount of stellar energy as our planet. These discoveries have fueled our imaginations and pushed our technology to new limits. They've helped us refine our understanding of planetary formation and evolution. But here's the thing. What if our Earth-centric view has been limiting us all along? You see, our focus on finding exact Earth analogs orbiting Sun-like stars makes sense from one perspective. We know life thrives on Earth, so looking for similar conditions seems logical. But the universe has a way of surprising us, of defying our expectations. And that's exactly what's happened with our latest discovery, the breakthrough discovery. Now let me introduce you to TOI 715b, the planet that's turning our assumptions upside down. TOI 715b orbits a red dwarf star about 137 light-years away from Earth. Now, I know what you're thinking. Red dwarfs aren't exactly known for their hospitality. They're smaller and cooler than our Sun, and they're notorious for their violent flares that could strip away a planet's atmosphere. But here's where it gets interesting. TOS 715b is located in what we call the conservative habitable zone of its star. This means it's in a sweet spot where liquid water could potentially exist on its surface, even accounting for the most pessimistic estimates. Let's break down what we mean by conservative habitable zone. When scientists calculate habitable zones, They often provide two estimates, a conservative or pessimistic estimate and an optimistic one. The conservative estimate assumes conditions that are less favorable for maintaining liquid water, while the optimistic estimate allows for a broader range of possibilities. Being in the conservative habitable zone means that TOI 715b has a high probability of maintaining conditions suitable for liquid water across a wide range of planetary characteristics. This is crucial because the presence of liquid water is one of the key ingredients we look for when assessing a planet's potential habitability. But that's not what makes this discovery so groundbreaking. Are you ready for this? TOI 715b is 1.5 times the size of Earth, making it a super-Earth. Now, super-Earths aren't uncommon in our galaxy. In fact, they're one of the most frequently discovered types of exoplanets. But finding one in the conservative habitable zone of its star? That's rare, really rare. To put this in perspective, most super-Earths we've found so far are either too close to their stars, making them scorching hot, or too far away, leaving them frozen. Finding one in the Goldilocks zone is like finding a needle in a cosmic haystack. But wait, there's more. The same star system might host another, even more Earth-like planet. This second planet, currently awaiting confirmation, is estimated to be only 1.05 times the size of Earth and orbits right at the inner edge of the habitable zone. Now I can almost hear you asking, haven't we found potentially habitable super-Earths before? What makes this one so special? Great question. And this is where things get really exciting. Why TOI 715b defies expectations. Let's break down why TOI 715b is such a game-changer. 1. The Goldilocks planet around a not-so-Goldilocks star. First off, TOI 715b orbits a red dwarf star. Traditionally, we've been skeptical about the habitability of planets around these stars. Red dwarfs, also known as M dwarfs, are the most common type of star in our galaxy, making up about 75% of all stars in the Milky Way. They're smaller, cooler, and much longer lived than our Sun, but they come with some significant challenges for habitability. Red dwarfs are known for their volatile nature, often bombarding their nearby planets with intense radiation and stellar flares. These flares can be hundreds of times more powerful than those from our Sun, and they occur much more frequently. This high-energy radiation can potentially strip away a planet's atmosphere over time, leaving its surface exposed to harmful cosmic rays. It's one of the reasons why we've been cautious about the potential for life around red dwarfs. But TOI 715b challenges this assumption. Its larger size compared to Earth might actually be an advantage here. A bigger planet likely means a stronger magnetic field and possibly a thicker atmosphere, both of which could provide better protection against stellar radiation. The stronger gravity of a super-Earth could help it hold on to its atmosphere more tightly, making it more resistant to atmospheric loss from stellar wind and radiation. Additionally, a thicker atmosphere could provide more shielding for the surface, potentially creating a more stable environment for life to develop and thrive. 2. The super-Earth surprise. Now let's talk about TOI 715b's size. At 1.5 times the radius of Earth, it falls into a category we call super-Earths. These planets, with masses between that of Earth and Neptune, are fascinating because they have no direct analog in our solar system. Historically, we've thought that planets this size might be more like mini-Neptune's gaseous worlds with no solid surface. This assumption was based on our understanding of planetary formation and the types of planets we've observed in our own solar system. But recent studies suggest that the boundary between rocky super-Earths and gaseous mini-Neptunes might be fuzzier than we thought. There's growing evidence that some super-Earths could indeed be rocky, potentially with thicker atmospheres than Earth, but still with a solid surface. TOI 715b's location in the conservative habitable zone makes it a prime candidate for a rocky super-Earth with potentially habitable conditions. If it is indeed rocky, its higher gravity could lead to some interesting possibilities. It could have a thicker atmosphere, which might be better at regulating temperature, and protecting the surface from radiation. The higher gravity could result in a flatter topography, potentially leading to shallower oceans, if water is present, spread over more of the planet's surface. Volcanic activity, which plays a crucial role in regulating a planet's climate through the carbon cycle, could be more intense and prolonged. 3. The potential for liquid water. Remember, TOI 715b is in the conservative habitable zone. This means that under a wide range of atmospheric conditions, the planet could maintain liquid water on its surface. Now, we haven't directly detected water on TOI 715b yet. Our current technology isn't quite there, but its position in this zone significantly increases the odds. And if there's one thing we've learned from studying life on Earth, it's that where there's liquid water, there's a potential for life. Water is crucial for life as we know it for several reasons. It's an excellent solvent, allowing for the transport of nutrients and waste products in living organisms. It facilitates many biochemical reactions necessary for life. It helps regulate temperature, both on a planetary scale and within organisms. The presence of liquid water on TOI 715b could create environments similar to those where we believe life first emerged on Earth, such as deep-sea hydrothermal vents or tidal pools. 4. A new kind of year. Here's something to wrap your head around. A year on TOI 715b lasts only 19 Earth days. That's how long it takes the planet to complete one orbit around its star. This short orbital period is actually a huge advantage for U.S. scientists. It means we can observe multiple transits in a relatively short time, allowing us to gather data much faster than we could for a planet with a longer orbital period. But it also has implications for the planet itself. The planet is likely tidally locked, meaning the same side always faces its star. This could create extreme temperature differences between the day and night sides. However, if the planet has a thick atmosphere or ocean, it could distribute heat more evenly across the surface, potentially creating a habitable zone along the terminator, the line between day and night sides. The rapid orbit could also lead to interesting seasonal effects if the planet's axis is tilted, with seasons changing every few Earth days. 5. The companion planet. And let's not forget about TOI 715b's potential sibling. If confirmed, this second planet would be even more Earth-like in size. 2 potentially habitable planets in one system. That's like hitting the exoplanet jackpot. The presence of 2 planets in the habitable zone could have fascinating implications for the potential development of life. Here are a few possibilities to consider. Could we be looking at a system where life could evolve independently on 2 separate worlds? This would be an unprecedented opportunity to study parallel evolution on a cosmic scale. Or could life, if it exists, potentially spread between the 2 planets? This idea, known as panspermia, suggests that life could be transferred between planets via asteroids or other space debris. The gravitational interaction between the 2 planets could lead to interesting geological effects such as tidal heating, which could provide energy for potential life forms. If intelligent life were to evolve in such a system, having a neighboring habitable world could spur the development of space exploration much earlier than it did for us on Earth. How we made this discovery. Now I know some of you are wondering, how did we even find this planet? Great question. Let's dive into the technology and techniques that made this discovery possible. Enter TESS, the Transiting Exoplanet Survey Satellite. Launched in 2018, TESS has been our eye in the sky, constantly watching for the telltale dimming of stars that indicates a planet passing in front of them. TESS uses what we call the transit method. When a planet passes in front of its star, it blocks out a tiny fraction of the star's light. By measuring these periodic dips in brightness, we can not only detect the presence of a planet, but also determine its size and orbital period. Let's break down how this works. 1. The amount of dimming tells us about the planet's size. The bigger the planet, the more starlight it blocks. 2. The time between transits gives us the planet's orbital period. 3. The shape of the light curve can provide information about the planet's atmosphere and even its moons or rings. But TESS doesn't work alone. Once it detects a potential planet, that's when the real detective work begins. Ground-based telescopes around the world spring into action, conducting follow-up observations to confirm TESS's findings. These observations help rule out false positives and provide additional data about the planet's characteristics. In the case of TOI 715b, researchers used a technique called high-resolution imaging to ensure that the signal wasn't coming from a background star or other cosmic phenomenon. This involves taking very detailed images of the star to make sure there are no other nearby stars that could be causing the observed dimming. They also used something called precise radial velocity measurements to estimate the planet's mass. The radial velocity method measures the tiny wobble of a star caused by the gravitational pull of its planets. This wobble causes slight shifts in the star's spectrum, which we can detect with extremely sensitive instruments. Here's how it works. 1. As a planet orbits its star, it exerts a gravitational pull on the star. 2. This causes the star to move in a small circle, or ellipse. 3. When the star moves towards Earth, its light is slightly blue shifted. When it moves away, the light is red shifted. 4. By measuring these shifts over time, we can determine the mass of the planet and its orbital characteristics. By combining data from TESS, ground-based telescopes, and these various techniques, scientists were able to build a comprehensive picture of TOI 715b and its potential companion. This multi-pronged approach is crucial in exoplanet research. It allows us to cross-verify our findings and build a more complete understanding of these distant worlds. Each method has its strengths and limitations, but when used together, they provide a powerful toolkit for exploring the cosmos. Implications for the search for life. Now let's talk about the big question on everyone's mind. What does this mean for the search for extraterrestrial life? To put it simply, TOI 715b and its potential companion have just significantly expanded our search parameters. Let's break down the implications. 1. Rethinking habitable zones. First, this discovery challenges our assumptions about habitable zones around red dwarf stars. If super-Earths like TOI 715b can maintain potentially habitable conditions, it means we might need to cast a wider net in our search for life. Red dwarfs are the most common type of star in our galaxy. If planets orbiting them can indeed be habitable, it dramatically increases the number of potential life-bearing worlds out there. This could mean that habitable planets are much more common than we previously thought. Moreover, it suggests that life might be able to adapt to conditions very different from those on Earth. The intense radiation environment around a red dwarf would pose challenges, but it could also drive unique evolutionary adaptations. Who knows what strange and wonderful forms of life could evolve under such conditions? 2. The potential of super-Earths. TOI 715b also highlights the potential importance of super-Earths in the search for life. These planets, with their stronger gravity and potentially thicker atmospheres, might actually be better at maintaining stable, life-friendly conditions over long periods. Here are a few reasons why super-Earths might be great candidates for life. Their stronger gravity could help them hold on to their atmospheres for longer, even in the face of stellar wind and radiation. They're likely to be geologically active for longer periods, which is important for maintaining a stable climate through processes like the carbon cycle. Their potentially thicker atmospheres could provide better shielding from cosmic radiation. This discovery encourages us to look more closely at super-Earths in habitable zones, as they might be some of the most promising targets in our search for life. 3. Multiple habitable worlds in one system. The potential presence of two habitable planets in the same system opens up fascinating possibilities. Could life evolve independently on two neighboring worlds? Could simple life forms be transferred between planets through asteroid impacts, a process we call panspermia? This scenario could provide a unique opportunity to study the development of life under slightly different conditions. If we were to find life on both planets, comparing their biochemistry could give us unprecedented insights into the nature of life itself. Moreover, the presence of a potentially habitable neighbor could have profound implications for the development of intelligent life. Imagine how differently our own space exploration might have developed if Mars or Venus were as habitable as Earth. 4. New targets for future missions. TOI 715b and its companion are now prime targets for future observations. The James Webb Space Telescope, for instance, could potentially analyze the atmospheres of these planets, looking for biosignatures, chemical signs of life. Biosignatures could include oxygen and methane existing together, which on Earth is a strong indicator of biological processes. Nitrogen dioxide, which could be a sign of industrial activity. Seasonal changes in atmospheric composition, which could indicate plant life or other biological cycles. The proximity of TOI 715 to Earth, only 137 light-years away, makes it an excellent candidate for these kinds of observations. This is close enough for our current and near-future technology to perform detailed studies of the planet's atmosphere and other characteristics. Furthermore, these planets could become targets for future interstellar missions. While 137 light-years is an enormous distance by human standards, it's relatively close in cosmic terms. As our technology advances, we might one day send probes to study these worlds up close. 5. Expanding our definition of Earth-like. Perhaps most importantly, this discovery encourages us to broaden our definition of what an Earth-like planet might look like. It reminds us that habitability might come in forms we haven't yet imagined. For instance, we might need to consider that life could thrive under much higher gravity than on Earth. The day-night cycle on a tidally locked planet would be vastly different from Earth's, potentially leading to unique adaptations in any life that might evolve there. The different stellar spectrum of a red dwarf star could lead to entirely different photosynthetic processes if plant-like life were to evolve. This expanded perspective is crucial as we continue our search for life beyond our solar system. It encourages us to keep an open mind and avoid being too Earth-centric in our expectations. Challenges and future research. Now, before we get too carried away, let's talk about the challenges ahead and the questions that still need answering. 1. Confirming the second planet. First and foremost, we need to confirm the existence of the second, more Earth-sized planet in the system. This will require additional observations and analysis. Confirming exoplanets, especially smaller Earth-sized ones, can be tricky. It often requires multiple observations over an extended period to rule out other explanations for the data we see. The process might involve additional transit observations to confirm the regularity of the signal, radial velocity measurements to determine the planet's mass, statistical analysis to calculate the probability that the signal is indeed caused by a planet. 2. Determining planetary composition. While we suspect TOI 715b is rocky, we can't be certain yet. Determining its composition will be crucial in assessing its potential habitability. This is one of the most challenging aspects of exoplanet research, as we can't directly sample these distant worlds. We'll need to use indirect methods such as precise measurements of the planet's mass and radius to determine its density, spectroscopic observations to analyze the planet's atmosphere, if it has one, models of planetary formation and evolution to infer the most likely composition. 3. Studying the atmosphere. If these planets have atmospheres, what are they made of? Do they contain gases that could indicate the presence of life? These are questions that will require more advanced observations, possibly from next-generation space telescopes. The James Webb Space Telescope, launched in 2021, is particularly well suited for this kind of research. It has the capability to perform transmission spectroscopy, analyzing the starlight that passes through a planet's atmosphere during a transit. This can reveal the atmospheric composition and potentially detect biosignatures. However, this is incredibly challenging work. The signal we're looking for is tiny. We're trying to detect minute changes in starlight caused by a thin layer of gas around a distant planet. It will likely require multiple observations and sophisticated data analysis techniques. 4. Understanding the star. We need to learn more about the host star, TOI 715. How active is it? How often does it flare? This information is crucial for understanding the radiation environment these planets face. Red dwarf stars are known for their flare activity, which can vary significantly from star to star. Some are relatively calm, while others have frequent powerful flares that could pose significant challenges for life on nearby planets. Studying the star will involve long-term monitoring of its activity levels, spectroscopic analysis to determine its composition and age, modeling of its magnetic field and how it interacts with its planets. 5. Long-term stability. Given the close proximity to their star, are these planets stable over long periods, or will tidal forces and stellar radiation gradually erode their atmospheres? This question touches on complex areas of planetary science, including orbital dynamics and the long-term stability of multi-planet systems, the evolution of planetary atmospheres under intense stellar radiation, the interplay between a planet's magnetic field, atmosphere, and its star's activity. Answering these questions will require a combination of long-term observations and sophisticated computer modeling. We'll need to simulate these planetary systems over millions or even billions of years to understand their long-term evolution. These are just a few of the questions that scientists will be grappling with in the coming years. And that's what makes this discovery so exciting. It's not an endpoint, but a beginning, a new chapter in our quest to understand our place in the cosmos. As we wrap up, let's take a moment to appreciate the magnitude of what we've discovered. TOI 715b and its potential companion represent more than just 2 more exoplanets to add to our catalog. They represent a paradigm shift in our search for habitable worlds. These planets remind us that the universe is often more diverse and surprising than we imagine. They challenge us to think beyond our Earth-centric views and consider new possibilities for what life and habitable worlds might look like. Consider this. Just a few decades ago, the idea of finding planets around other stars seemed like science fiction. Now we're not only finding them by the thousands, but we're starting to characterize them in incredible detail. We're on the verge of being able to study the atmospheres of distant worlds, to search for the chemical signatures of life light years from Earth. This rapid progress is a testament to human ingenuity and our relentless curiosity about the cosmos. It's a reminder that we're living in a golden age of astronomical discovery, with each new finding pushing the boundaries of our knowledge a little further. But perhaps most importantly, discoveries like TOI 715b reignite our sense of wonder and our drive to explore. They remind us of the vast unknowns that still exist in our universe, waiting to be uncovered. Every new exoplanet we find is a world of possibilities, a new frontier for our imagination and our science. As we peer into the night sky, let's remember that each point of light represents not just a star, but a possibility of worlds beyond our imagination, of life in forms we've yet to dream of discoveries waiting to be made. So keep looking up, keep asking questions, and keep exploring. Because out there in the vast expanse of space, Earth 2.0 is waiting, and who knows, it might be more incredible than we ever dared to hope. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell, and let me know in the comments, what kind of life do you think could exist on a super-Earth like TOI 715b? Your ideas might just inspire our next video. Until next time, stay curious, stay skeptical, and keep reaching for the stars.